In this video, we are going to do another induction proof. So this one is going to involve an inequality. So the example says, let h subscript n represent 1 plus a half plus 1 over 3 plus dot 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 plus 1 over n. So it's the sum of positive numbers where I keep making this denominator getting bigger by 1. Okay, so for example, h subscript 3 would be 1 plus 1 half plus a third. Okay, so there's a key calculus fact which says that if we let n get infinitely large, the sum that we have above, 1 plus a half plus a third plus a fourth and so on, this gets infinitely large. And this is a bit unusual since as n gets infinitely large, we end up adding terms that get closer and closer to. So these fractions that we get as you get further and further out, they get closer and closer to 0, because you get 1 over a really big number. That's eventually going to get really close to 0. So eventually, as you get really far out, you just add things that are getting really close to 0 again and again and again. So it might be a little weird about like, well, why is it getting infinitely large? Okay. One of the key steps that you need to prove that is to show that if I take 1 plus a half plus a third plus a fourth and so on up until some point, and the point I'm going to stop at is 1 over 2 to the n power, that will always end up being greater than or equal to 1 over n over 2. In calculus, you discover more about like, why does that show that if it goes on infinitely, why is it going to be infinitely large? It has to do with the fact that if this side is always bigger than this side, it turns out this side is much easier to analyze. As n gets infinitely large, this numerator gets infinitely large, so this fraction does, and adding 1 to it makes it even larger. So this whole thing will get really big, infinitely big, if n gets infinitely big. And this side is even bigger, so that means that's also going to get infinitely big. Okay, so let's prove this fact here. Okay, so this left-hand side, notice that is just h subscript 2 to the n. So whatever this subscript is, that is this final denominator. Okay, I'm going to show that is greater than or equal to 1 plus n over 2 for all positive integers n. So I'm going to start with some scratch work here. And in the scratch work, I'm really going to focus on the inductive step. So the inductive. So remember, in the inductive step, we assume that p of k is true, and then we try to show that means p of k plus 1 is true. Okay, so before I get into this, let's first just say what it is that we're doing. So in my proof, I'm going to proceed by induction on my variable, which in this case is n. And the very first thing we do is we identify what p of n is, the statement that we are trying to prove. So for our problem, p of n is that 1 plus a half plus a third plus a fourth plus dot 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 plus 1 over 2 to the n power always is greater than or equal to 1 plus n over 2. And then just for short, we are calling this whole left-hand side h subscript, whatever this biggest denominator is. So for us, that's 2 to the n power. Okay, that is my p of n that we're trying to prove. Okay, so we begin these induction proofs with the base step. So in the base step here, well, what is the starting point? I'm trying to show that this is true for all positive integers n. So my base step is n equals 1, because that's the first positive integer. So what I do is I work out both of the sides here. So my left-hand side is if I plug 1 into it, if I plug 1 into this, we get h subscript 2 to the 1, which means that's just h subscript 2, because 2 to the 1 is 2. So to evaluate that sum, we start at 1, and you keep going until you reach this term as the denominator. But that's going to be the very next thing, because this very first term is 1 over 1. So the next term will have a denominator being 2. Okay, so if I add these together, I get 3 halves. All right, so now let's look at the right-hand side. If I plug 1 in to the right-hand side, we end up getting 1 plus 1 half, which is also 3 over 2. So, okay, I got these two sides. So notice that the left-hand side is greater than or equal to the right-hand side here. So the base step holds. Okay, awesome. So we've shown the base step. Now we move on to the inductive step. And this is where I'm going to be doing my scratch work, because the inductive step is really the heart of the problem. That's where the hard stuff is. Okay, so in the inductive step, we start off by letting k be an arbitrary element of whatever set we are working with. So in my problem, I'm trying to show it's true for all positive integers n. So, all positive integers. So I'm going to say k is an arbitrary positive integer. K is an element of the positive integers. Okay, so this just comes from, well, what is the set that we are working with in our problem? So for me, it's positive integers. Okay, and then I assume in the inductive step that p of k is true. Okay, so before I say what is that, at this point let's do some scratch work. Let us do some scratch work. So in the scratch work, because I have this if-then statement, remember what I get to assume, I'm going to add that to this column, my assumptions is that p of k is true. So what is p of k? P of k is, let's take this statement and let's plug k in to both sides. So I'm going to put a bullet point there. So that would be that 1 plus a half plus a third plus ... plus 1 over 2 to the k power, that ends up being greater than or equal to 1 plus k over 2. So this left-hand side is what we are calling h subscript, and the subscript is whatever this last denominator is, 2 to the k. Okay, so that is what we're given. That is what we get to assume is true. We assume p of k is true. And what I want to show is that, I want to show that p of k plus 1 is true. P of k plus 1. So for p of k plus 1, I take k plus 1 and I plug it into both sides. So that would give me 1 plus a half plus a third plus ... And eventually, my denominator will be 2 to the k plus 1 power. So that's much bigger than even this denominator. So 1 over 2 to the k plus 1 power. I'm deliberately leaving some space. And the reason why I'm leaving some space is, earlier in this sum, because this denominator is bigger than 2 to the k, somewhere earlier in the sum, we will run in one of the previous terms will be 1 over 2 to the k power. And then after that, I make the denominator be bigger, and I'll get plus ... plus until finally I reach this ending point. Okay, and what is the other side? The other side of this statement, if I plug in k plus 1 for the n, becomes 1 plus, instead of n over 2, it's k plus 1 over 2. So that is what I want to show. Okay, so due to conciseness, I am going to just show how we would do this, not in the scratch work, but in the actual proof. Because these induction videos tend to be longer, just because induction proofs tend to be a bit longer. Okay, so, all right. So in my inductive step, we were at the point that we assume that p of k is true, namely that, and this is what p of k is. So we are going to be assuming that 1 plus a half plus a third plus a fourth plus ... plus 1 over 2 to the k is indeed greater than or equal to 1 over k plus 2. Okay, so we assume that's true for any positive integer k. For an arbitrary positive integer k. Okay, so now what I'm going to do is, now I'm going to consider just the left-hand side of the inequality that I'm trying to prove. I'm just going to start off by writing it down. So I'm just going to consider 1 plus a half plus a third plus ... Eventually I'll get to 1 over 2 to the k. Let me write some more terms this time. After that, the next fraction would be 1 over 2 to the k, and then whatever that is added to 1. And then the next one would be 1 over 2 to the k, and then plus 2. And then so on, plus ... And eventually the denominator will reach this denominator. Eventually it'll reach 1 over 2 to the, And in the exponent is k plus 1. Notice how this term is different from this one. This one's 2 to the k power, and once we work out 2 to the k, then I add the 1. Whereas in this one, the whole k plus 1 is the exponent. Okay, so I'm considering just the left-hand side of what it is that we're trying to show. So I really want to somehow be able to show that this whole thing ends up being greater than or equal to 1 over k plus 1 over 2. So here is the big idea. The type of thing that I have is, I'm adding fractions that kind of look like this, like 1 over 5 plus 1 over 6 plus 1 over 7 plus 1 over 8, where I keep just making these denominators like go up by 1. So here's an idea of how I can start to introduce an inequality into this. If I had something like this, what if I just took each of these fractions and made the denominator bigger, either bigger or kept it the same? So I changed the 5 to an 8, changed the 5 to an 8, and then I changed the 6 to an 8, and I got 1 over 8, and I changed the 7 to an 8, and I got 1 over 8, and then the last one, let's just keep it the same as 1 over 8. So the last fraction stayed exactly the same. The other fractions, I've made the denominator bigger, so that makes each of those fractions smaller. That's why if I add all of these 1 over 8s together, this whole thing is going to be less than or equal to what I started with. So I'm going to use this idea that if I'm adding a bunch of fractions like this, and I make certain denominators bigger, it generates an inequality like this. It'll end up with fractions that end up being smaller than what I started with. Okay, so I'm going to put a thought bubble around this. The other key idea behind this, which I forgot to mention earlier, but let's mention it now, is in terms of this thing that I'm looking at, one of the things I notice is the thing that I get to assume is true, p of k, I see one of the sides showing up. I see that showing up right here. 1 plus a half, all the way up until plus 1 over 2 to the k. I know that that is greater than or equal to. 1 plus k over 2. So that's nice. I just need a way to be able to handle the remaining terms, because the remaining terms don't show up in this. And for the remaining terms, that's where I'm going to be using this idea of, let's just change the denominators to make them bigger. And that gives me an inequality. Okay, so when I do that, what I get is, I start off by writing the things that I had initially. Okay, so let me say this. Let me give myself a little bit more room. Let me not write more than I have to. So remember that this whole thing that I had here, this was h subscript 2 to the k plus 1. That's just my shorthand notation for this sum. So what I have now is that h subscript 2 to the k plus 1. Let's replace these first terms that I have here with this thing that I know is less than or equal to it. So when I do that, this whole sum will end up being greater than or equal to, let's replace this with the 1 over k plus 2. So in other words, I'm replacing this with something that's smaller than it. That's why the inequality looks like this. And now I got to think about, with these remaining terms, I'm going to do this denominator trick. Let's make each of their denominators bigger. So I'll get 1 over something plus 1 over something plus ... plus 1 over something. And now each of those denominators, let's do kind of like what I did here. Let's change it to the biggest one that I see in the list. Well, the biggest one I see is this last one. So I'm going to change all of them to that last one. 2 to the k plus 1. So I'm changing all of them to 2 to the k plus 1. Okay. And now, all of these terms that I'm adding at the end, they're the exact same number. So to add them together, I just need to know, how many of them are there? Well, if I look at this original sum that I had, because my subscript was 2 to the k plus 1, that means in this original thing, there were 2 to the k plus 1 terms. Whatever that is, that many terms. In this first portion, up until 1 over 2 to the k, within that, there were 2 to the k terms. So that means in this portion at the end, this portion over here, there's going to be, well, we subtract those two numbers. I'm running out of room. Let's do it underneath. So over here, there's going to be 2 to the k plus 1 minus 2 to the k terms. But I can simplify this because I can factor out 2 to the k from each of these. If I factor out 2 to the k, I'll be left with 2 and then minus 1. And that is just 2 to the k times 1, which is 2 to the k. We will have 2 to the k terms. So nice. There are 2 to the k terms here, and they also end up being 2 to the k terms there. Turns out if you add 2 to the k to 2 to the k, you will get 2 to the k plus 1 if you do a little factoring. Okay, so that means in all of these things I have added up at the end, there are 2 to the k terms here. 2 to the k terms here. So I'm almost there now. So what that means is I can say this whole thing is greater than or equal to, let's copy down the first part, 1 plus k over 2. And now for this next part, well, if I'm just adding the same thing to itself, a bunch, 2 to the k times, what I'll end up getting is that term times 2 to the k. So I will get my 1 over 2 to the k plus 1, but it gets multiplied by 2 to the k, because I added the same thing to itself 2 to the k times. Okay, so, well, 2 to the k divided by 2 to the k plus 1, that simplifies. This simplifies. I can cancel a 2 to the k, and I'll be left with 1/2, actually. And if I add these together, this now equals 1, and then k over 2 added to 1/2 becomes k plus 1 over 2. So if I look at what I have on one side is h subscript 2 to the k plus 1, which is this entire thing. Sorry. That was this whole original thing here. And then I started using some inequalities. So when I did that, I got it's greater than or equal to some stuff. And then I got that's greater than or equal to some more stuff. And eventually that simplified down to this. And that is precisely what we wanted to show. I eventually wanted to show that it will be greater than or equal to 1 to the k plus 1. Sorry, 1 plus k plus 1 over 2, which is what we ended up getting. Okay. So that is what we wanted to show. I just got to state my conclusion, which is by induction. By induction, the thing I wanted, h subscript 2n, that was this sum over here. Well, that does end up being greater than or equal to 1 plus n over 2 for all positive integers n. Okay, so that completes the proof, and we are done.